Go ahead.
Okay. Hello, everyone. My name is Fang. I'm a PhD student of Hunan University, and my tutor is Professor Guangzai Gong. The title of my presentation is Transferability Investigation of Deep Reinforcement Learning Control Strategy in the Building HVAC System Level. My presentation mainly includes the following 4 parts. First, let's look at the research background. HVAC systems account for about 45% of building energy use. The energy consumption of non-optimal control scheme in HVAC system can be up to 13% of the air conditioning energy consumption. And HVAC system strategy optimization is an effective way to achieve the building energy conservation. Currently, HVAC system control methods mainly focused on the rule-based control and the model-based control. The rule-based control methods don't consider the dynamic changes of the environment and HVAC systems, and generally fail to obtain an optimal system control performance. The model-based control methods, such as the model predict control, need to construct the system model and highly relies on the model accuracy. When the model is not accurate enough, the performance may divert from the expectations. In addition, the scalability of the traditional HVAC control method is poor. For new buildings, systems, and climate zones, models are difficult to be reused and need to be remodeled, which greatly increase the modeling effort and time. Model-free control methods such as the reinforcement learning can be used to greatly improve the model reusability. Model-free reinforcement learning methods have the characteristics of model-free self-learning and online learning. It can reduce the dependence on prior knowledge by interacting with the environment and automatically learn the optimal control actions with the feedback word. Reinforcement learning is also a feasible solution for optimal control of HVAC systems, and it has been extensively studied in recent years. However, the repetitive training of deep reinforcement learning control strategy for different HVAC systems is laborious. There are few studies to discuss this weakness. Therefore, it's necessary to find a way to improve the training efficiency of the reinforcement learning control strategy. Reinforcement learning combines with the deep neural network named as the deep reinforcement learning. And the transfer learning can transfer the knowledge learned from a source task to another related task, and it is a feasible way to utilize the transferability advantages of the neural networks. With this idea, transfer learning can transfer the pre-trained parameters of some network to the target network and reduce the cost of modern training. Then let's look at the methodology. Reinforcement learning mainly concludes of the agent, environment, action state, and the reward function. The agent learns to execute optional actions by interacting with the environment. It is aimed to maximize the cumulative rewards, thus obtain the optimal control actions, such as the temperature set point sequence. In this study, the different control algorithm is used for HVAC control. Transfer learning is to transfer the knowledge learned from the task to another related target task. In this study, the fine-tuned based transfer learning method are used. It can reuse some parameters of the pre-trained network to the target task. And this figure shows the reinforcement learning for building HVAC system control. It contains 2 main loops, including the control loop and the learning loop. The control loop is the DQN agent to obtain the state, and in a certain state, the learning loop is to update the DQN parameters by the agent. And then we proposed transfer learning and deep reinforcement learning integrated framework for the building HVAC control. The whole framework contains 3 steps. First, the DQN is penetrated in the source building until it covers to an optimal strategy. Then the well-penetrated work of the first few layers are transferred to the target DQN. Finally, the target DQN parameters of the last few layers are fine-tuned in the target building. And the optimal control process of the reinforcement learning is as follows. The reward function of the energy consumption and the temperature violations is defined first. Then the DQ values are calculated based on the reward function. Finally, the mean-square error between the target and the estimated Q values are used as the loss function. The weight parameter in the DQN are updated by the gradient descent method. As the whole process are completed in the simulation environment, and the LH+ is normally difficult to apply the DQN control algorithms in the built-in software. The Python is used to implement the DQN control algorithm. This code simulation testbed are developed to realize the data transmission between these 2 models. This figure shows the detailed implementation diagram of the developed code simulation testbed. LH+ model is wrapped into a functional mock-up unit model. The DQN control module is implemented by Python. PyFMI is a Python package which supports loading with the FMU models for code simulation. And this figure shows the overflow chart of our study. It mainly includes the following 4 parts. And then I will show the results and discussions. And the large multi-zoo office reference building with VAV systems are used to evaluate the proposed deep reinforcement learning control strategy. The supply air temperature and the chilled supply water temperature are regarded as the DQN control actions. 3 large office reference buildings from Denver, Austin, and Houston are used for the experiment settings. And the 3 buildings transferred pairs with each other and form the following 3 transfer scenarios. In addition, as transferring the different number of layers has the great effect on the control performance. Therefore, the control performance of transferring the different number of layers are also discussed and evaluated. 3 performance evolution metrics are used to evaluate the transferability of the DQN control strategy. First, the robustness is the standard deviation of the cumulative rewards energy consumption and temperature violation. The DQN training efficiency construct is the average DQN training time of each episode, and the control performance is the average energy consumption and the temperature violations. And the model hyperparameters have great effect on the model control performance. First, the near optimal model hyperparameter should be first determined based on the results of the convergence robustness and the control performance of the DQN baseline models can be respectively determined. Then let's look at the results. This figure shows the DQN control results. It can be seen that the 2 controlled temperature can be keep a stable values after some episodes, and meet the meantime, the trade DQN control agent can find a proper trade-off between the energy consumption and the indoor air temperature violation with the selected control temperature set point, and that is the performance is in a near optimal control region. These results show the effectiveness of the DQN control strategy. After the DQN control performance are verified, then the transferability of the DQN control strategy between different HVAC systems are evaluated. we take the results of the experiment of Denver transfer to Austin as an example. This figure shows the calculative reward average consumption and the temperature variations of the Denver transfer to Austin. And it can be seen that for the Tier 2 model, the control performance of Denver transfer to Austin maintained the same level as that of the baseline DQM model. This figure shows the training time for transferring the different number of layers. It can be said with the number of transferring layers increasing, the DQM training time decreases. This is mainly because more parameters are frozen and fewer parameters need to be trained. This table shows the all transfer performance evolution matrix of Denver transfer to Austin. The performance evolution matrix with smaller values show better performance. That is the values in the bold red of this table. The Tier 2 model has the best comprehensive transfer performance. Finally, let's make a conclusion. Firstly, an Energy Plus Python consummation testbed is developed based on the FMI standard, which can implement the advanced model-free-based deep reinforcement learning control algorithms in a simulation environment. Secondly, a transfer learning and deep reinforcement learning integrated framework is proposed for control strategy transfer of building HVAC system, which can effectively improve the deep reinforcement learning training efficiency in the building HVAC system level. Secondly, DQM-based multi-objective optimal control strategy can effectively find a proper temperature set point sequence to achieve the trade-off between the energy consumption and the indoor air temperature in a multi-zone building system. Finally, the proposed transfer learning and deep reinforcement learning model performance is sensitive to the number of network layers. Comprehensive analysis of the transfer performance evolution matrix, the Tier 2 model has the best comprehensive transfer performance. And that's all for my report. Thank you for your attention.
Yeah, thank you, Fang. Any questions from the audience?
Yes.
Yeah, sure. Go ahead. Yeah, go ahead.
Hello.
Hi, hello.
I have a question. What you don't use it the software Transys for simulation? Because Transys is very efficiency of Python and Energy Plus design builder. Because for me, I work with PCM and building, and I have a simulation from design builder and Transys and Python, and I have comparison from the three application. Transys is very efficiency from design builder and Python.
And okay, we use the Energy Plus Python co-simulation mainly considering two factors. First, the Energy Plus software is easy to build the building HVAC systems, and the Python is also easy to implement.
Yes. From the mathematical, you enter the intern and external, the input and output from temperature and capacity and density from the materials, because the civil engineering you use the different materials and you change the characteristic from the two application.
Okay. I think the software,
because in Transys you can simplify the characteristic from the materials. You can measure the building from AutoCAD and integrate and transit and present the characteristics from materials, and you have efficacy simulation from the building and
Okay.
from the you can use the SCPS application from the infrastructure, the road and the electric.
Okay, thank you.
Okay.
Okay.